Okay, so this will be on mathematical induction. In geometry, you would have talked a little bit about deductive and inductive reasoning, but this is on mathematical induction. Okay, and basically on these, they're going to go through to prove, as an example, they will ask you to prove problems like this: 1 plus 3 plus 5 plus 7. They're giving you a series, plus, and then dot 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 to show you left out terms, plus the quantity 2n minus 1, and that equals n squared. They want you to prove that that's true, and prove that it's true for all natural numbers, okay, for n. And you can sub in, you can say, okay, let's say if n was 2. If n was 2, then this would stop at 3 on this side. So 1 plus 3 would be 4, and if n was 2, 4 equals 4, yeah, that's true. Try 3. If you put 3 in, okay, then this stops at 5, and you'd have 1 plus 3 plus 5 would be 9, and 3 squared is 9, yeah. But you have to prove it for all natural numbers. That's just given 2 examples worth, okay? So, to prove something by mathematical induction, there's actually 2 cases that you have to go through. Okay, to prove something by mathematical induction. Okay, the first thing is you must prove it works for the number 1. And they consider this the trivial case. And you'll see why in a minute. Okay, so you have to show that it works for the first number, for natural numbers 1. Okay, the second step, you have to assume that it works for any positive, arbitrary, k, and show it works for k plus 1. A lot of authors will call this like the domino effect. If you think about, and you can go on YouTube and find the domino videos where they set up all the dominoes and tap one and it knocks them all over. First you have to show it works for the first domino, so that would tip it over. But then if you go in and pick any domino in there, okay, and then show that it works for the next one, okay, then it works for all of them, okay? Some authors will think of it as like a ladder effect too, and say, okay, show that you can get on the first rung, and then from any rung up above you can get to the next one, okay? Okay, I want to go back to this, okay, and take you through proving this by mathematical induction. Okay, so just repeat this, and in the book, it will have it as a prove. Notice in the original problem, it's an n. Okay, prove that it works for true for all the natural numbers. Okay, and I use PF for proof. Okay, and there's 2 parts. On part 1, that's the trivial case. Okay, and that is to show it works for 1. Okay, so to show it works for 1 is on the left side. You just substitute in 1. So if you put in 1 in there, you're going to have 2 times 1 minus 1 equals 1 squared. So 2 minus 1 is 1. 1 squared is 1. Checks. Okay, and that's why it won't take much to show it works for the number 1. You just, everywhere you see an n in the original, you're going to substitute in a 1.
Is it just the number 1, or is it
I'm just taking and subbing in a 1 right there. That's all you do. Okay, and I sub it in on both sides. Okay, and they show that they are equal. Okay. Okay, part 2. Okay, now this wording, it doesn't have to be word for word, but it's got to be close enough that it means the same. Okay, and by the time you get through the homework, hopefully you would have written this enough times you have it memorized. Assume 1 plus 3 plus 5 plus 7 plus, show the 3 dots, plus. Now here's where it differs. In the original problem it's an n. Okay, when you start going through the proof, you substitute in a k everywhere you see an n. So you'd have 2k minus 1 equals k squared. So all I'm doing is I'm subbing in for this n, I'm subbing in a k. Okay, assume that is true for any positive, arbitrary k, and show, okay, assume that that is true for any positive, arbitrary k, and show it is true for k plus 1. That's kind of the intro statement for part 2. Now you actually do the algebra. Okay? When you do the algebra, you do 1 plus 3 plus 5 plus 7 plus ... plus 2k minus 1. Okay, and we need to show it's true for k plus 1. So you need to go one more term on the left side. So plus, to go one more term, everywhere you see a k up here, okay, up here, you're going to substitute in a k plus 1. So this would be 2 times the quantity k plus 1 minus 1. Okay, and it equals, then on the right side, everywhere you see a k, you're going to put in a k plus 1. So on the left side, basically we just put in one more term. Okay, we put in that term. And on the right side, we just substitute everywhere you see a k, you put in a k plus 1. Okay, now, take this off a minute. Okay, if you look, this whole thing is equal to what? K squared. Isn't this the same? So you will always use substitution. Okay, k squared equals this whole thing. So I ought to be able to substitute k squared in for all of this. You will always use substitution on these. So k squared plus, now simplify, this would be 2k plus 2 minus 1. So that'd be 2k plus 2 minus 1 plus 1 equals k plus 1 quantity squared. Now, you have a choice, and I will tell you on some of the proofs, you have a choice. I could multiply out that right side, square out the right side, or I could factor the left side. I will tell you on some of these proofs, it is easier if you factor than if you take the time to multiply it out. And that goes all the way back to look for what's in common, difference of two squares. Okay, for this one, it really doesn't matter. But I subtracted the 1. Yes, because I'd have 2k plus 2 minus 1. Yeah. Okay. So I can go either way. I can go k plus 1 quantity squared on the left, or I can go k squared plus 2k plus 1 on the right. Doesn't matter. Okay. I'm going to just factor. That will factor back. What you have to do is you have to work the left side and the right side down until they are equal. These will always work. They will always be equal. If yours aren't equal, then you've got a mistake. Okay? It's not a question of will they work or won't they work. They will all work. Okay? But I would make a note out at the side. Sometimes factoring these from here to here, sometimes factoring is easier than to multiply it all out. And you'll see what I mean on the proofs. So that's the algebra part of it. Okay, this is kind of like the intro statement here. And you have to write that intro statement. When I'm grading these on the test, I'm looking for the trivial case, the steps, I'm looking for the intro, I'm looking for the algebra, okay, and then I'm going to look for the conclusion. Okay, so once you get those true, we proved that it works for the first number. We assumed it worked for any positive arbitrary k and showed it worked for k plus 1. Now it works for all n's. Okay, so this is the conclusion statement. In geometry, you should have used the 3 dots. The 3 dots mean therefore. Okay, now you have to write the conclusion. And basically, you just go back up to this intro statement and put it in past tense. Okay, so we assumed 1 plus 3 plus 5 plus 7. Leave the 3 dots plus. Okay, you still put in 2k minus 1 equals k squared. We assume that. Now change it to past tense. Here's your English coming in. Past tense. Assume that was true for any positive arbitrary k. Okay, we assume that was true for any positive arbitrary k and showed, change it to past tense, and showed it was true for k plus 1 I guess I put a comma there, period there. Therefore, okay, it is true for any. Okay, now look up here a minute. All of these were k's. It's true for any n, an element of the set of natural numbers. Okay, that means it's going to work for any natural number. Okay. Okay, so that conclusion, we assumed that that was true for any positive arbitrary k and showed it was true for k plus 1. Therefore, it's true for any n, an element of, that means an element of is an element of the set of natural numbers. Okay. Now, notice on this, and I will get picky on this. Okay, the n appears up here in the first, in the proof, in the problems. Okay, n is right there. All the rest of them are k's. Okay, makes sense? Okay, that's one problem. Okay, welcome to upper level math. Okay, I'm going to give you the rest of the time. If you're basically the intro statements, are going to be identical. The conclusions are, same idea. It's can you do the algebra in between and get them equal. Okay, and like I said, some of them I would not multiply them out. I would do factoring. Okay, but if you're not getting left side equals right side, then you need to ask some questions. Okay.